Welcome back. In this lecture, we will talk about evaluating and selecting unsupervised learning methods with a focus on clustering. So here's our objective. So selecting a clustering algorithm. So common practice is to really just run several different approaches and use different distance functions, use different scaling techniques, and if there's other hyperparameters or things change such as how a centroid is computed, try those as well. So selecting a clustering algorithm is really all about validation and hyperparameters or things that are like hyperparameters. It's also highly domain dependent, and this makes a lot of sense. If you think about earlier, I talked about how computing an average is essentially an unsupervised method. Whether or not average is useful in a given situation really depends on what that situation is. So there's two types of methods to evaluate clustering algorithms. One is through the use of ground truth, and the other is through cluster measurements. Now, the thing you may ask about with ground truth is, well, if I have ground truth data, why not just use the supervised approach? And there's a couple good reasons why you may not use a supervised approach. And one may be that the distribution of the data does not lend itself to most supervised approaches. Your data is not IID, for example, or when something gets labeled, it's because it's an outlier. So in cybersecurity, for example, outlier detection, finding something that's new and malicious is usually done with unsupervised methods because the bad guys are constantly making new malware that's going into these networks. Meanwhile, people are buying new software that creates different baselines. And so supervised methods don't do as well in some of those environments compared to unsupervised. Now with cluster measurements, the question you may ask is, well, isn't the clustering algorithm trying to optimize with respect to a certain measurement? And that is true, but you can use one or multiple cluster measurements to augment that as well. The other thing about cluster measurements is they can be used to measure a specific cluster. So your output of your clustering algorithm may provide K-1 really good clusters and one that's sort of, loose or not very tight for whatever reason. So let's talk about the ground truth comparison. So the underlying assumption is each class is corresponding with a cluster, and so the technique is to use a confusion matrix to compare the class labels of the data with the clusters. Now, unlike with a supervised approach, the clusters are not saying, hey, it's in cluster 1, therefore it must be in the positive class. The clusters don't tell you that information, so you got to kind of figure that out with whatever metric you use. And so, while you can use precision and recall and all that, you have to also do that other step. But using measurements like entropy, where you can look at each cluster and you can make this following measurement that tells you, how pure the cluster is in terms of representing a single class as opposed to many classes. And then you could take a weighted sum of the entropies and you could get the total entropy for the set of clusters. An alternative to this is a measurement that's just called purity. And here it's a little bit simpler. You're just taking the class that is most represented in that cluster and what fraction of that cluster belongs to that class. And purity can be also shown for the set of clusters as well using the same kind of weighted sum that we saw for entropy. But the intuition, both of those, they're looking at for individual clusters how pure an individual one is. So you don't need to go right toward total purity or total entropy. You can actually examine each individual one And this is useful from an analytical perspective as well, because you may have certain clusters that are pure within a class, and then you may have some that are much less so. So there might be something about a given class in that cluster where maybe there is a special subgroup of samples within that class that caused them to cluster together, and then others fell outside and fell into kind of this miscellaneous cluster. So, of course, in most of the time dealing with clustering, we're probably not going to have ground truth, so we should look to measure cluster quality. The silhouette coefficient is one such method, and A is the mean distance from, or AI is the mean distance from point I to all other points in the same cluster, while B is the mean distance between I and all points in the nearest other cluster. And so by looking at this, and you can also plot this out for individual clusters or the individual samples as well, and this kind of gives you a feeling for quality of the clusters. Indirect evaluation is, this is getting back to the underlying domain. And the concept here is often clustering is not really used as the primary task. It wasn't just to say group something, but maybe it was to divide samples, and then those samples were going to go into a supervised model that would then classify the data. And so if you're doing something that is staged like that, then indirect evaluation is referring to how well the overall system does on the other task. And so you may even have where the clusters don't turn out to be that great, but it causes the entire system to work better. Indirect evaluation, might be the way to go. Also in here, you could actually think of the clustering method itself as being kind of a hyperparameter in the development of the overall system. So anyway, this concludes our discussion on evaluating clustering techniques. Thank you.